Hello, welcome to another module in this massive open online course. So, we are looking at SDP, that is semi-definite programming, and its application in the context of MIMO detection, that is how to reduce the complexity of the MIMO detector, that is the maximum likelihood detector. Okay. So, we are looking at SDP for MIMO ML detection rather. Okay. And SDP employs an interesting constraint. If you remember this is a positive semi definite constraint, that is that basically this matrix has to be, this linear combination of matrices has to be positive, so positive semi definite. This is termed as a linear matrix inequality, LMI. Okay, so SDP is interesting in the sense that it employs a matrix inequality. This is a linear matrix inequality. As SDP enforces a linear matrix inequality, that is what is novel about SDP. And we are specifically looking at this MIMO detection problem, where we have a received vector y bar minus h is the MIMO channel matrix h x bar square, and we have to perform argmin, that is minimize, that is find the x bar belonging to this set S which minimizes y bar minus h x bar square. And the problem with this is, if you look at this set, the cardinality of the size of that set is basically m raised to t, where m is the number of symbols in the constellation. Okay. And of course t, this is equal to the number of transmit. T equals number of transmit antennas, and so basically this is exponential in the number of transmit antennas, which has a very high complexity. Okay. So this is exponential in number of transmit antennas. So how can SDP help in this context? For SDP, what we do is, let us simplify the cost function. This is y bar minus h x bar square. This is your objective. Objective function or cost that has to be minimized. Okay. And I can write this as follows: y bar minus h x bar, this is norm square of a vector. So I can write this as vector transpose times itself. Okay. So I can write this, proceed by writing this as y bar minus h x bar transpose y bar minus h x bar. This simplification we have seen previously also, so I will go fast over this. Y bar minus y bar transpose minus x transpose h transpose into y bar minus h x bar, which is equal to y bar transpose y bar minus x bar transpose h transpose y bar minus y bar transpose h x bar plus x bar transpose h transpose x bar. Okay. So this is basically the cost function, simplified cost function. Now here I am going to do something interesting. I am going to write this as follows and convince yourself this can be written as the following thing. Okay. This can be written as equivalently as x bar transpose 1. So I am making a column vector. So x bar I am stacking it along with this number 1. So I am making it t plus 1 dimensional column vector, okay, x bar transpose 1, and this matrix I can write this as H transpose H minus H transpose y bar minus y bar transpose H y bar transpose y bar times x bar 1, okay. And if I call this t plus 1 dimensional vector now S bar, or rather S bar transpose, this I call as S bar, this I can call as the matrix L, okay. And therefore what I have is, I have this vector S bar which I am defining as x bar 1, this is a t dimensional and this is, so this is single element, so this net vector will be, this vector will be t plus 1 dimensional and if you look at this vector, this is a matrix L which is given as follows. So L is the matrix which is given as follows, this is H transpose H minus H transpose y bar minus y transpose H, and this is y bar transpose y bar, okay. So therefore we have this matrix L, and therefore now I can write this basically, if you look at this, this is S bar transpose L into S bar. So we have written this as S bar transpose L into S bar. So I have recast this as a weighted norm minimization problem, that is, we have written this in the form of S bar transpose L times S bar, where L can be thought of as a weighting matrix, okay. And now I can equivalently minimize this, so I can minimize this S bar transpose L S bar, okay. So I can minimize S bar transpose L S bar. However, the only problem here is that of course we have constraints. Now what are the constraints? Now remember, if you look at S bar, still we have, I mean the problem, we have just recast it, the problem has not changed. We still have, if you look at S bar, which is x bar comma 1. So if you look at S bar, so if you look at the ith element, okay, so your for 1 less than or equal to I less, so if you look at the ith element, that is Si, for 1 less than or equal to I less than or equal to T, that still has to belong to the constellation. So let us say this is BPSK constellation, so this has to be plus or minus 1, okay. So these elements, that is the first T elements, are still the symbols, that is x1 x2 up to xt. So remember, these still have to belong to the constellation, that is each of these can only take two values, that is plus or minus 1, which is where the problem is arising in the first place, alright, because you have this large number of vectors over which you have to search. Now I am going to manipulate this cost function in a step by step. First note that each magnitude Si square, in fact for the t plus 1th element is also 1, so all magnitude Si square equals unity, or in fact in this case simply considering real symbols, you can note that simply Si square equals unity, okay. So if you look at S bar transpose, which is basically S1 S2 up to St plus 1 into its transpose S1 up to St plus 1. If you look at the diagonal elements of this, so this is not a diagonal matrix, but if you look at the diagonal elements all the diagonal elements will be, there are also off diagonal, these are the off diagonal. But if you look at the diagonal entries, all the diagonal entries are equal to 1, because each SI square is 1. Therefore, all the diagonal elements of this S bar transpose are 1, are unity. Okay. Now, what I am going to do is basically, now you realize the first thing, as we have shown these two are equivalent. So, minimize norm y bar minus h x bar square can be equivalently written as minimize S bar transpose L S bar. Okay. Each SI belongs to still this symbol of plus or minus 1, assuming BPSK, binary phase shift keying, and for of course 1 less than equal to I less than equal to T. Now, what I am going to do here is, now I am going to employ this thing. So, now first step 1, observe that S bar transpose L S bar, this is a scalar quantity, this is a number. So, I can write this as trace, because if you take the trace of a number, remember trace is the sum of the diagonal elements for a square matrix. So, a single number is a special case of a square matrix. So, the trace will yield the number itself. So, this I can write this as trace S bar transpose L S bar. Now, using the property trace AB equals trace BA. So, this becomes trace of L S bar transpose, which I can now write as trace L times S, where what is S? S equals the matrix S bar transpose, which is of course positive semi definite, because I can express this as S bar transpose, and diagonal of S equals, basically you have all the elements are unity. So, this has to be this vector 1 bar, and further we have seen that S is positive semi definite, S is greater than equal to 0. So, now I can equivalently formulate this as, so equivalent problem will become minimize, the equivalent problem is minimize S bar transpose L S bar subject to the constraint, or in fact not minimize S bar transpose L S bar, I apologize, this is minimize trace of LS subject to the constraint that S is a positive semi definite matrix, that is S is greater than or equal to 0, or first let us write the diagonal. So, diagonal of S equal to unity or not unity, that is each element of the on the diagonal of S is 1. So, diagonal of S is 1 bar, the vector of 1s. S is a positive semi definite matrix. Okay. So, S is positive semi definite. Further, S can be written as S bar transpose. Now, of all the constraints, this is the most difficult non-convex constraint. Because it is non-convex. This is known as a rank 1 constraint. This is known as a rank 1 constraint because S equal to S bar, as that is single vector expressed as a vector S bar transpose. So, whenever you have a vector matrix of this form, which is vector times its transpose, then it is basically rank 1 constraint, and this is a non-convex constraint. So ensuring this is very difficult, or constraining this optimization problem using this rank 1 constraint is very difficult. So what we do is, naturally what we do when we encounter something difficult or difficult to impose, we simplify it. In this case we simply ignore this. This is known as an SDP relaxation. Okay, so we relax it. So this rank 1 constraint makes it non-convex, or it makes it non-SDP. So we relax it as an SDP, that is, ignore this rank 1 constraint. So what we do, ignore the rank 1 constraint. So we ignore the rank 1 constraint. Obtain SDP. This is termed as SDP relaxation. This is termed as SDP relaxation. Okay. So what we have now is an interesting problem, that is, we can equivalently, so our ML decoder can be equivalently written as ML MIMO decoder for that matter. Can be equivalently written as minimized trace of LS subject to the fact that diagonal S equals the matrix of ones, S is positive semi-definite, and that is it. Okay. And this yields an approximate solution. So this is significantly lower complexity. So now from exponential complexity we have come to a convex. Now this is a convex optimization problem. Okay. Now this problem is convex. In fact, this is an SDP. It has a linear matrix inequality. So this is an SDP. Convex. This is an SDP. Now while the original problem is exponential, this problem has much lower complexity. This has much lower complexity, and therefore it is very amenable to implement this in practice, very suitable for practical implementation. The only thing is, it yields an approximate solution, of course. It is a solution that is actually shown to be very close to the optimal ML solution. So this yields approximate solution. Close to the ML solution. Okay. Now once you find S, now once you find S, how to find S, or how to find S bar rather. So the point is, you find this matrix S, S equal to S bar transpose, but it is not guaranteed because we have ignored the rank 1 constraint. Not S is not guaranteed to be a rank 1 matrix. S is not guaranteed to be of the form S bar transpose. So now since we have ignored it, S is not guaranteed So S is not guaranteed. So in this context, how do you find S bar? It's very simple. The answer is very simple. Find the best rank 1 approximation to S. That is the key here. Find best rank 1 approximation. Find best rank 1 approximation to S. For that, implies we use the eigenvalue decomposition of S, and this is also very interesting. How do you find the best rank 1 decomposition of a matrix, of a square matrix or a symmetric matrix? Use the eigenvalue decomposition. Remember, the eigenvalue decomposition is as follows. I can write S as Q lambda Q transpose, where Q is the matrix of eigenvectors, and this is diagonal matrix of eigenvalues. This is the diagonal matrix of eigenvalues, and then I can write this as summation I equals 1 to n plus 1 lambda I qi bar transpose, where lambda I equals ith eigenvalue and qi bar equals the ith eigenvector and therefore this is simply nothing but lambda 1 q1 bar transpose plus lambda 2 q2 bar transpose plus lambda 3 q3 bar transpose. Now, since this is positive semi-definite, since S is PSD, note that lambda i's are greater than or equal to 0. This implies lambda I is greater than or equal to 0. So, I can always arrange them in decreasing order, alright. So, these lambda i's are real quantities, in fact, they are greater than or equal to 0. So, I can always arrange lambda 1 greater than or equal to lambda 2 greater than or equal to lambda 3, so on. So let lambda 1 greater than or equal to lambda 2 greater than or equal to lambda 3 and so on. So, implies lambda 1 equals maximum eigenvalue. Then the best rank 1 approximation is simply this, that is you choose S equal to lambda 1. So, ignore the rest, okay. Just simply choose S equal to the largest eigenvector, outer product of eigenvector corresponding to largest eigen. So, best rank 1 approximation is simply S is approximately equal to lambda 1 q1 bar transpose, which I can always write as square root lambda 1 q1 bar square root lambda 1 q1 bar transpose, which is now equal to here S hat transpose. So, S equal to, or rather S hat equal to S hat transpose, and the final step is S equal to, remember your vector x bar comma 1. So, that implies S hat equals x hat comma 1, okay. So, by choosing the first t symbols of S hat, you get transmitted symbols x in x bar, okay. So, by choosing one can estimate or detect rather the transmit symbols x, and from that of course you can get the transmit vector x. That is how you basically, so you take the original ML decoder, right, recast it in a different form alright, and then you relax. The critical thing here is that relax the rank 1 constraint, that makes it a semi-definite program. This process is known as SDP relaxation. From the SDP relaxation you get S, which is a positive semi-definite matrix. From that you perform the eigenvalue decomposition, but get the best rank 1 approximation. So that will give you, in fact there is nothing but the principal eigenvector, alright, the scaled principal eigen given in terms of the scaled principal eigenvector of S. From that you take the top T symbols, those are your ML estimates. Alright, so let us stop here and continue the subsequent modules. Thank you very much.